Well, hello. I think we're going to get started. It looks like we have a few people still coming in, but for the most part, I think everybody who's interested in hearing about AllJoyn over MQTT is probably already here. Can you all hear me well enough? Good. Yes, was that a yes? I couldn't hear you. Let me bring the microphone down so you can. Okay. So I'm just going to give you an introduction, a little bit about the rationale, what we did, and then Sheshambika is going to take over, and we're going to do quite a technical deep dive. So hold on to your hats, strap yourself in. The more you know about AllJoyn, the more sense this will make, but I think that hopefully you'll get value in it one way or another anyway. So let's get started. So we're going to talk a little bit about the rationale, just some MQTT basics for just a couple of slides for those of you who don't necessarily know what MQTT is, and then we're going to sort of dive into the technical details. So, what are we doing? AllJoyn was designed primarily to focus in the short term on proximal networking use cases, devices that are in close physical proximity on the same subnet, and the protocols that were chosen, such as MDNS for discovery, were all sort of based around the assumption that we were going to be connecting maybe hundreds of devices. We've now started to think about industrial IoT use cases and smart city type use cases, and so we're doing what we have been talking sort of generally as the 1000x challenge. How do we go from hundreds of connected nodes or connected devices to hundreds of thousands of connected devices? And the current architecture of AllJoyn is not going to scale to those kinds of levels without a massive amount of rework. And it turns out that MQTT is an existing server technology that has already been developed to a point of maturity where it does scale to those kinds of scales. So we really kind of set out with, you've got to think of what this work, by the way, as an experiment or a prototype. I don't want to give anybody the impression that this is a complete and finished work, and although you can certainly use it and play with it, it's going to evolve because we're sort of the early stages of what we're doing here. But we set out to answer this question: can an MQTT broker replace an AllJoyn routing node? And the approach that we've taken is to modify the thin client code to communicate directly via MQTT messages, and the MQTT broker takes care of the message routing. So instead of having an AllJoyn routing node routing the messages, we're going to let an MQTT broker do that. We had a set of requirements. These are kind of requirements we set for ourselves as we went into this experiment. First of all, we wanted it to be transparent to the application code. So existing AllJoyn applications based on the thin client code base should still work. It must support about-based discovery because that's the way that discovery is used now by applications. It must support sessions, including multipoint sessions, and it must support sessionless signals because these are all features of AllJoyn that are becoming more and more heavily used, and pretty much any sophisticated application depends on these. So why did we want to do it? MQTT, as I said, is designed for high scalability. Benchmarked at 1,000 times the number of connections supporting by an AllJoyn routing node. Some implementations are claiming more than 200,000 simultaneous connections, and we see numbers like 1 million messages per second through very highly optimized, configured, running on big iron, and And there's a lot of work gone into robustness, scalability, and so on. There are multiple broker options. There are hosted options, there's SaaS solutions, and there are open source solutions. Our intent is that you do not need to change the broker. The broker, we will work with the existing brokers. And then there are dozens of client libraries, many open source, Mosquito, RSMB, WebSphere, MQ, HiveMQ. A lot of libraries, and some of them are open source. Just a couple of slides and some MQTT basics. Basically, in MQTT, clients communicate with what's known as an MQTT broker. It's a server. The broker handles all the communication between the clients, and brokers can communicate with other brokers. The protocol is message-based pub-sub. MQTT does not define a payload format. And this is actually one of the reasons why AllJoyn and MQTT fit so well together. MQTT doesn't care about the payload, and AllJoyn is really all about the payload. A message is published to a broker and is tagged with a topic. A topic is a simple /delimited hierarchical text string. Messages can be also made persistent by setting a retain flag in the message, in which case they get stored in the broker. A client can subscribe to a topic by essentially providing a string that is either an exact match or has some wildcarding in it. So you can send messages into the broker sometimes will store them, and then you can send message to the broker saying, give me messages that match this pattern, more or less. Next. MQTT clients specify a unique client ID when they connect to the broker. Clients can optionally disconnect while maintaining all of their existing subscriptions. So actually you don't have to have the connection stay live all the time, which is something that we've certainly taken advantage of. And clients can define what's known as a last will, or a last will and testament, which is a message that gets published automatically by the broker on behalf of the client if the client disconnects in a surprising fashion. So the TCP/IP connection goes away, basically. Client can only specify the will once, and there's only one will. We've used all of these mechanisms, retain messages and will and so on, in the implementation of AllJoyn over MQTT, as you will find, which is why we're mentioning it. A published message, a way to cancel a published retained message is to simply publish to the same topic with a null message body. And there's plenty of information on, just Google MQTT. There's plenty of information, mqtt.org, if you want to get the technical details. But we just thought that a couple of slides to give you the basics. So, Sheshambika, I'll let you take over.
Thank you, Greg. So let's go over some high-level overview of AllJoyn over MQTT. So as Greg mentioned earlier, we wanted it to be transparent to application code. So what we did was had a shim layer, a code shim layer that sits beneath the whole application layer. And now instead of sending AllJoyn messages, what it does is publishes the message. That is, the whole payload would be the message, the AllJoyn message, to a particular topic. And on the other hand, instead of receiving, what it does is subscribes to the appropriate topic. Thin clients connect directly to an MQTT broker, and standard clients still connect to a router that connects to a broker. There is a similar code shim layer on the standard client router as well. We have one more application, which is called a Scavenger. Now, MQTT does not support timeouts for retained messages, nor does it clean up, the protocol does not define cleanup of messages when a node leaves the network. So essentially what the Scavenger does is takes care of these two things on behalf of clients. It can run on the same machine as the broker, or it could run on a different machine. As far as the broker is concerned, the Scavenger is just another client. What's been contributed so far, we have an experimental thin client and router implementation that's available on the feature/MQTT branch. It builds on Linux, Windows, and Darwin. And it links to the Mosquito open source library, which is BSD licensed. It maintains the same APIs. There are no new APIs. One major difference to note is that AllJoyn routing nodes are discovered via MDNS, whereas the configuration to a broker is currently defined at build time. We do not have any client-to-broker authentication as of now, but the AllJoyn peer-to-peer security model will still apply. So let's look at the typical topology in the case that there is one broker in the system. So as we see here, that is the broker. Here is the scavenger that will take care of cleaning up the retained messages. We have thin applications here that connect directly to the router. And these are the standard applications that connect to either a standalone or a bundled router that connects to the broker. Brokers can be configured to forward certain messages over certain topics to other brokers. So this is the topology wherein two brokers are connected to each other and all the messages can be routed. So what is supported so far? We have support for direct messaging. How that works is every node in an AllJoyn system has a unique name. And using that, we came up with a topic that is the unique name topic for that node. So all nodes subscribe to their unique name topic, and that way all other nodes can directly send messages to the node by using that topic. The current implementation supports sessionless signals, and how that is done is sessionless emitters will publish the whole payload, the message, that is the whole sessionless signal, as a payload to a particular sessionless topic, and the retain flag is set to true. Sessionless receivers will subscribe to a wildcarded sessionless topic, and the broker manages these subscriptions, and it forwards messages as applicable. About-based discovery is a special case of sessionless signals, wherein it uses the interface org AllJoyn about and the member name announce for discovery. Well-known name discovery is not supported on this branch. The other important feature that we wanted to support was sessions. The session joiner can discover the session host by using about-based discovery, and I will get into more technical details about that in the later slides. Following which, the session joiner sends a join session or an accept session to the session host by using the unique name topic. And on the provider end, that is either the provider thin client library or the provider router, sends an accept session call to the application. So as far as the application is concerned, the behavior is just as it would be today in case of AllJoyn. Depending on the application's response, the provider's thin client library or the provider's router will send the join session or accept session response back to the consumer. Both ends subscribe to a session topic, which is used for session cast messages, that is, messages that are sent with a null destination and a particular session ID. So let's look at some implementation details. Before we go ahead, I wanted to talk about a couple of terms. One is the scope GUID. Now let's say we have an interconnect of about 10,000 nodes. Not all of them would be interested in talking to every other node. So the scope GUID is used to filter out that communication. As we see here, the scope GUID is at the starting of all the topic strings. And the other concept that I wanted to talk about is the GUID and number here, mentioned here. So an AllJoyn unique name is of the format :x dot a number. Typically, the router is the one that assigns the unique name to all its clients. One thing to note is that in this case, the thin client does not connect to a router and it directly connects to the broker. So the thin client uses a persistent GUID to come up with its own unique name. To distinguish a thin client from other thin leaf node that's directly connected over MQTT, what we did was set that number to be 0 for a thin leaf node. And always routing nodes are the .1, and anything above that is a standard client leaf node that's connected to a router. So the presence topic, the presence signal, is used by other nodes to detect whether a particular node is still on the network, that is that node still connected to the broker? So the format for that is the scope GUID, followed by the presence string literal, and then the GUID and the number of the node. The direct destination topic is the unique name topic that I mentioned before, and that is the scope GUID, followed by the GUID, followed by the number. The session cast topic that is used for session-based messages is the scope GUID, followed by the session ID, followed by the host's GUID and number. And the session list topic that I mentioned before is basically the scope GUID, followed by the providers, that is the session list emitters, GUID and number. And at the end, we see the interface and member of the session list signal. The last will that we used was a presence signal with a null payload that indicates to all other nodes on the network that a particular node has left the network. In addition, what it does is gets rid of that retained message, as a result of which the presence signal is cleared. So here's how sessionless signals work. Sessionless signals use the session list topic. And as I mentioned before, the retain flag is set to true. Emitters publish the whole payload to a sessionless topic, and receivers subscribe to the wildcarded topic. So let's look at a typical about discovery flowchart here. So as we see here is the connect. The thin client connects to the library, as a part of which the library connects to the broker, and it sets the last will. In addition, it subscribes to the unique name topic and publishes presence. So that is done by both ends. One key difference to note here is that since the thin client is not connected to a router, it must manage all the session port information locally. So that is done here. Now let's say the client adds an add match that is turned into a subscription to the wildcard about topic. That would be the scope GUID followed by the ++ to indicate anyone is announcing itself. And here is an announcement from the provider that generates the announced signal, and then that signal is published to the about topic. Since the broker at this point knows that this consumer is interested in that signal, it forwards the announced signal, and that is delivered to the application. So about-based discovery for standard client applications is very similar. One key difference is that at the time of connect, this is all related to the router, whereas previously it was related to the application. So the last will is for the router, and the subscription is also for the router. Other than that, this is quite similar. The other difference that I wanted to note here is that when the announced signal is sent out, the subscription for the provider is made, so that in the future, if any node wants to communicate with the provider, that will be received by the router on behalf of the provider. It also publishes the presence for the provider and publishes the announced signal. So now let's look at a point-to-point session establishment use case. What happens is that the first part is a join session or accept session. There are 4 possible combinations. One is a thin client consumer trying to join a thin client provider, a thin client consumer trying to join a standard client provider, a standard client consumer trying to join a thin client provider, and the last case is a standard client consumer trying to join a standard client provider. So the only case that uses the attached session message, because it needed more information, is the standard client to standard client join session. So that in that case, an accept session message is used. In every other case, the join session message is used. On the remote end, that is the provider end, the library or the router will generate an accept session callback. And depending on the response, a session ID may be generated and the response is published back to the consumer. In addition, both ends subscribe to the session cast topic. So here is the session establishment between a thin client and a thin client service. I do have a few slides about the other 3 use cases, but I'm not going to go over that for this presentation. So as we see here, the first step is the about-based discovery, followed by the join session API being invoked by the consumer. What the library does at this point is fills in the message destination to be the session host, and it publishes the join session message to the provider's topic, which is forwarded by the broker. And as we see here, an accept session is generated, and depending on the response, a join session response is sent back to the consumer. As we see here, both ends now know the session ID and they know the session topic. One additional step is that both ends subscribe to the other end's presence topic, because if the other end leaves abruptly, then that needs to be detected as a session lost. This end gets the session join callback, and this end gets the join session reply. So as far as the application is concerned, there is no change in functionality. Multipoint session establishment is quite similar to point-to-point, but there is one additional step because MP session change signals need to be sent out. So 2 steps involved in that, one being the provider has to send the MP session change signal for the new joiner to any existing applications, and it needs to update the new joiner with all the existing applications in the session. So this is the multi-point session establishment. Up until this point, the process is quite similar to a join session, a point-to-point join session. I wanted to highlight the 2 extra steps here. One is that the provider publishes the session member changed for the new consumer to the session topic, which is forwarded to every application that is already in the session. So the provider gets that and issues a MP session change to the provider application. Similarly, the consumer 1 gets that and publishes the session change to the consumer 1. This is the catch-up that I was talking about. So the provider sends out the MP session member changed signal for the consumer 1, which is the already existing consumer, to consumer 2. And here we see the MP session member changed being sent out to the application. So the next topic is about how to leave what happens when some node leaves a point-to-point session. What it does is it publishes a session lost message to the session topic, and the other end that was in the session receives that. It cleans up the session allocated session, and it sends out the session loss to the application. So as we see here, the about discovery followed by session establishment. Now let's say the provider leaves the session. So it invokes this leave session API, as a result of which a session lost message is sent out to the session topic. It is received by this end, and both ends unsubscribe from the topic. This session lost is forwarded to the application. Leaving a multi-point session is similar, but the difference is that an MP session member changed is sent out instead of a session lost. One additional step needs to happen, which is every application, if it's a thin client, then the thin client library will take care of this. If it's the router maintains the list of all applications that are in the session. Now, if a particular node is the last member in the session, a session lost needs to be sent out. And that tracking is done on both thin client library and the router. So this is at this point, the whole session has been established. This end does a leave session, as a result of which the MP session change is sent out and forwarded to both the provider and to the consumer one. And both the applications receive the MP session changed for consumer 2. Now let's assume that the provider leaves the session. Now, MP session changed for the provider is sent out to the session topic, received by this consumer, and it is sent out to the application. In addition, since this is the last member in the session, it publishes a session lost to its own unique name topic. And that round trips back from the broker, and it is sent to the application. The other thing that happens is, on leaving the session, all ends unsubscribe from the session topic. As I was mentioning earlier, there is a presence signal, and the last will is used for detecting that a node has left the network. So what happens is, when a node leaves the network, the broker sends out the last will to all its connected nodes that are interested in that topic. And when that is received, the applications will clean up the session and send out session changed or session lost as applicable. So let's look at the flowchart here. So as we see here, this is the discovery and session establishment. Now, let's say at this point, the connection from consumer 2 to the broker is lost. What happens is, the broker sends out the last will to the consumer's presence topic. So since all ends subscribe to the other end's presence topic at the time of session establishment, both the provider and consumer 1 receive that last will. And they publish a session changed to their own unique name topic. That is, consumer 1 publishes an MP session changed for consumer 2 to consumer 1 topic, and the provider publishes the same message to the provider's topic, which is forwarded back by the broker. And both ends, that is, the producer and the consumer 1, receive that session member changed signal. The next topic I wanted to talk about is the scavenger. And the scavenger is responsible for 4 tasks preliminarily. One is getting rid of sessionless signals that have timed out. The second task is to get rid of sessionless signals when a node leaves the network. The other point to note is that since standard client applications connect to the broker via a router, if the router to broker connection is lost, it is equivalent to the standard client applications being disconnected from the network. So when that happens, the scavenger will publish a null, thereby getting rid of all the sessionless signals for all the nodes that were connected to that router. In addition, it does also clean up presence signals for the nodes when their router leaves the network. There are couple of more slides detailing the scavenger, but I'm not going to go into that for this presentation. So let's look at some test results from tests we've done so far. We've had success with stress applications joining and leaving sessions continuously and sending method calls and session signals. We've also had success with a multipoint session having about 1,000 nodes in session, and all of them receive the MP session changed signals as appropriate. We've had success with some about-based discovery cases. The first experiment we did was a single consumer and 2,000 producers, all connected to a single MQTT broker. And what we saw is that the consumer receives the about signal for all the 2,000 producers. The other use case we did was to have 3,000 thin applications and 3,000 standard applications connect to two brokers. So 1,500 of them would connect to broker one, 1,500 would connect to the other one, and configure the brokers to forward messages over the appropriate topics. And we saw that all of those nodes were both emitters and receivers of about-based signals. That is, they would publish their own announcement, and they would be interested in the about announcement from all the 5,999 other nodes. And we saw 100% signal reception with that use case. That's all I had for this presentation, so please let me know if you have any other questions.
So you didn't mention the QoS parameter when you publish MQTT messages. Which one do you use?
The one that we use is QoS 0.
0.
Yeah.
So that means you have no reliable delivery of messages.
That is correct. As of now, that's the one.
And do you deal with them in any special way? Any ways of retransmitting messages, or is that not necessary?
It's a complicated, it's a more complicated question than you make it out to be, actually. It's not that you don't get reliable delivery of messages. I mean, that's not quite what QoS 0 means, right? So,
It means at most once delivery of messages.
right. But if, with method calls, we probably would continue to use QoS 0 because we have the round trip, and in that case, if the method call succeeds, then the reply comes back. For signals, we probably want to be moving to a QoS 1, but we haven't done that yet. As I said, this is experimental. So the other thing that we should point out is one thing that may have come across is that the whole session establishment stuff is somewhat complex. We think that we may use this as a way of experimenting with some alternative approaches to session management. I know that we've discussed a little bit on the core working group about wanting to go to a peer-based session type model. And I think that it would certainly help here. But I think that's something that probably we should do independently of MQTT, but it would certainly be beneficial in terms of the flows that we see for MQTT. I will also point out that this is, although what we've done here is MQTT, anything that has the same kind of pub-sub type architecture as MQTT could probably be substituted fairly easily. Any other questions? Yes, Dominique?
Yeah, I'm going to be the annoying one here. So what I didn't really, I can shout. So
Can people back up there hear? Can you hear the questions at the back?
No.
No. When you have to go behind the speakers, otherwise it'll squeal.
Okay. So damn, now I lost my question. Let me think a second. All right, so what I didn't really catch from the presentation was, is it possible to have an AllJoyn network without any routing node now, with just MQTT brokers?
If they are thin applications, yes, that is possible, without any routing node.
Yeah, so no routing nodes at all. Would it be possible, in that case, to just say, going to the future, we just drop the routing node completely? You don't need it. That's a lot of complexity in core that maybe you can drop entirely and just replace by an MQTT broker and a smaller shim at the standard clients, thin client library level, basically, because it would significantly reduce the code complexity.
Yes. But. Okay. Yes, but. So yeah, When we decided we would integrate the thin library because it's just quicker and simpler. It's a smaller code base, and it was much easier to do that. But we have an existing, we're building an existing ecosystem of devices. We've got devices that use routing nodes. We have, Windows 10's got routing nodes in. We've got standard clients. So the solution that we've come up with is kind of, I think, a little bit the best of both worlds. We have got some code that allows all of the nodes behind a routing node to appear to all the other nodes, whether they be directly connected to the broker or connected via a routing node, to see each other, right? Without adding a great deal of complexity to the routing node. And yet, at the same time, we can create a network that consists of nothing but thin library nodes, eliminating the routing node altogether. So I think that, my feeling is, my initial sort of a concept for this was that we would just do the thin client and replace the routing node. And then, once we started thinking a little bit more about it, Sheshambika and I were discussing it, we said, well, it's not that hard to look at bridging the routing node in. And of course, now we've got this ability to merge the proximal network and everything we get there, including interoperability and backwards compatibility and everything we've done so far. And I can still have a device out here that's maybe connected via a cellular modem, bridge into, connect to a broker, and be part of my network, right? So we're allowing for, we're really thinking far more about industrial IoT use cases in terms of scalability and in terms of flexibility, as and of course you heard this morning in Kiva's keynote that's an area that we think is really the next frontier for AllJoyn. Any more questions? I think we're just about out of time, actually. Maybe one more question if anybody has one. If not, yep.
Could you talk to the difference between using XMPP versus MQTT?
The question was, can I talk to the difference between using XMPP and MQTT? Okay, there's kind of two parts two answers to that question. One is Affinity's got an XMPP connector for the AllJoyn gateway agent. And in that case, they're using XMPP as a mechanism for discovery and tunneling, which is a different use case than we're describing here. But beyond that, I'm not sure I can answer the question. I've not really spent any time with XMPP. If somebody has more familiarity with XMPP, they might be able to answer that question, but I don't. Yep. You want to introduce yourself, Mr. XMPP?
Andy Stanford-Clark from IBM. I designed MQTT. I think that's the... So I'm probably quite well qualified to answer this question. So XMPP, if you look at the traffic, is got lots of XML and HTTP headers and stuff. MQTT was deliberately designed to be compact on the wire and sort of non-chatty in the protocol. So if you have any concerns about either buffer lengths on a constrained device or network bandwidth on the wire, if you're paying for it by the byte, then MQTT was designed to be much more efficient. You can do it using XMPP because that's a similarly pub-sub thing, but it was designed as a instant messaging chat protocol, and it shows if you look at the packets that are flying around. So it's just much more efficient to use MQTT in terms of the network bandwidth and the chattiness.
Thank you for bailing me out. Okay, I think we're out of time now, but hey, thank you all for coming in and listening. We weren't sure that going into such a deep technical discourse here was going to have such a mass appeal, but this is a good sign. I'm very encouraged. Thank you. And thank you, Sheshambika.